Hello, we're back to talk about problem number 13, and this problem takes us back to the Planck distribution again. And we're going to demonstrate that the Planck distribution reduces to the Rayleigh-Jeans law at long wavelengths. So to recall, the Planck distribution is defined as energy density and all of this stuff. So this is the Planck distribution. So when we're considering long wavelengths, we're looking at this guy. And we're looking at this really more than this wavelength to the fifth, because this exponent value is basically what controls, well, it really just fixed the problem with Rayleigh-Jeans law. So because this is the reason that it fixed the ultraviolet catastrophe, this is the value that we're going to be looking at. So when we consider long wavelengths, we can see that the value hc over wavelength kt gets really small, a lot smaller than 1. And that's because it's in the denominator. So bigger denominator, small result. So we can make an approximation for this quantity inside the parentheses as the wavelengths get long. So we can approximate and replace. So for this quantity, e to the hc over wavelength kt minus 1, as wavelengths get long, we can sum up how these values change, and we get an approximate value of just the exponent, hc over wavelength kt. And this is explained in more depth in Atkins, so if this is confusing, I have it in my chapter 7 in the section where it talks about the Planck distribution. Anyways, so if we just algebraically replace this quantity with this, everything simplifies to Rayleigh-Jean. So substituting back into Planck distribution, we have eight pi hc over wavelength to the fifth times hc over wavelength kt. So we get, I'm just going to separate this out into two multiplied fractions so I can see better. 8 pi hc over wavelength to the fifth times reciprocal wavelength kt over hc. So hc's cancel. We get a fourth, wavelength to the fourth instead, and we get 8 pi kt over wavelengths to the fourth, which is exactly Rayleigh-Jeans law. Which is pretty cool.